The term work is yet another example of physics as a foreign language that sounds a lot like English. Work has a very specific meaning in physics. Now, when an external force is applied to a system of particles, it has the ability to change the energy of that system. And so a definition of work is that the energy is transferred to a system when an external force is applied to an object in that system and the object is displaced, so it moves in the direction of the force. Okay, when we apply a force to, say, a box and we push it along, so there's our normal force, and there's no other forces acting on that box, we find that the energy of that box will increase, its kinetic energy will go up. So we're transferring energy to the system that is that box by applying a force, and the object is displaced in the direction of the force. In the next example, we have a box which is sitting on a surface, and there is friction between the box and that surface, so we apply a normal force, but of course there's a force of friction. Now, if we consider the box and the table to be the system, and we apply a force with the finger, and of course, just say we're pushing that box at a constant velocity, we're not adding any macroscopic kinetic energy to the system because it's going at a constant velocity, but we are transferring energy to the system because of that frictional force there. You've got energy stored as internal energy of the box and of the table. And so your internal energy will increase. Right, the third situation is if I am lifting a box, say with a string, the system that I'm interested in is of course not just the box, because it needs to include the earth because of that gravitational interaction there. So the box is feeling a force due to gravity, and the external force applied is pulling the box upward. We are, of course, increasing the potential energy of that system, so the gravitational potential energy of that system. Positive, sometimes we say positive work is done. So positive work basically means that the energy of the system increases, and that happens when the external force is acting on the system and it causes that change, that you've got a change or an increase in the energy of the system. In order for this to happen, the force that you're applying needs to be in the same direction as the displacement that is happening. And you can actually see that in all those cases that I've given above, in all of them, the displacement of the box is always in the direction of the external force. So in all of these cases, the energy of the system is increasing. Now, negative work, sometimes it's referred to as negative work, is when the energy of the system that you're considering is decreasing. And what that looks like is where the system itself is doing work on its surroundings. So in this situation, the external force that's being applied is in the opposite direction to the displacement of the particle that's in that system. And I'll try and explain here by using this middle example up the top here. Just say this box was already in motion, and it was in motion towards the left of the screen there. So it's coming towards that hand, and now the hand is being placed there to stop the motion of the box. So it's pushing against the box in order to stop it. There is an external force being applied, but that force is to the right, whereas the displacement of the particle is to the left. So in that case, the force is causing a change in the energy of the system, but it's essentially the system applying a force to the outside, which is causing that system to lose energy. So in this case, the external force is opposite direction to the direction of motion, so it's slowing down, which means our work is negative, which means we have a loss of energy from the system. We'll go through another example of these when we talk about conservative and non-conservative forces. All right, there is of course an equation. Work is the change in energy of the system, and it equals the force times the displacement times the cos of the angle between those force and displacement vectors. So just in a few notes there, that's the force, it is in newtons. The displacement that happens while that force is being applied is of course generally in meters, and that's the angle between the force and the displacement vectors. The neat thing is that when that theta value is 0, so when the force and the displacement are pointing in the same direction, cos of 0 is 1, so you'll have the maximum work being done there if they're in the same direction. If they're at 90 degrees to each other, cos of 90 is 0, so no work will be done. If we've got 180 degrees here, so the force is in the opposite direction to the displacement, then you actually get a negative value for work, which means you get energy lost from the system, which fits in nicely with our definitions. Work is just a change in energy, and so it has the units of energy, which are joules, or you can see from that equation that the units of work must equal the units of force times the units of displacement, which is of course Newton meters, or those can also be converted into kilograms meters squared per second squared. One other thing that you will need to know about work is that it equals the area under a force displacement graph, and you can look at that. If you have force on the vertical axis and displacement on the horizontal axis, the force times the displacement will just give you the area of the rectangle if it's a constant force. And so I'll give you that example first. Here is the example, work as area under the force curve. So here's your force displacement graph. Work equals the force times the displacement, and so it's that area under there. Now if you have say a force which is changing, so in the next example we've got a linearly increasing force here, you can essentially break that down into lots of little rectangles and add them all up, and that's integration, that's calculus, and so it's just the area under the curve. And even more calculus looking is the final example there, where you've got a curve where it's changing with time, and this is just the integral of that curve, so you've got the area under the curve.